All right, I'll just take 1 minute to introduce our speaker. So we're happy to have Sayan Bhattacharya who is currently an associate professor at the Department of Computer Science at the University of Warwick. Sayan did his PhD from Duke University and his postdoc at NPI at the University of Vienna. And also after a brief stint at Institute of Mathematical Science in Chennai, India, Sayan joined University of Warwick. Sayan has been working in graph algorithms and specifically dynamic algorithms, and he has been doing excellent work consistently for more than a decade now, including Best Awards in SODA this year and also ICALP in 2021. So today Sayan is going to give us just a glimpse of the recent advances made in the dynamic graph algorithms, specifically dynamic matching. So very happy to have you. The stage is yours.
Thanks, Nick, for the invitation and also the introduction. So as the title suggests, I'm going to talk about recent advances in dynamic matching. Let me start with a few disclaimers. So first, in the talk, I will not assume any prior background on dynamic algorithms whatsoever. And I will often skip the strongest version of a result and instead present the more intuitive and weaker version to make the talk more meaningful. And I will often make claims that I will call LFMT, and I think this is an abbreviation that should become more popular, just like WLOG. LFMT means literally false but morally true. Okay. So now let's start with an introduction. So what is a dynamic algorithm? So take your favorite computational problem and take any algorithm for it. Suppose on a given input I, the algorithm comes up with an output O. In the dynamic setting, we ask what happens if now the input changes by means of a small update. And after this update, the algorithm needs to come up with the new output, which also changes slightly. And this keeps happening again and again. So the input keeps undergoing a sequence of updates. After each update, the algorithm has to accordingly adjust its output. Now the time taken to handle an update is called the algorithm's update time, and we wish to design an algorithm with as small update time as possible. There is a trivial answer here. Just run a static algorithm from scratch on the new input after each update. That would give you an update time that is equivalent to the static runtime. In the dynamic setting, we ask, can we do something significantly faster? And note that you can ask this question in the context of any optimization problem or any computational problem. So why do we care about dynamic algorithms? I'll try to give a few reasons for it, even if you are not working in dynamic algorithms. So the first reason is, I hope that the question is very well motivated. So in real world, if you look at Google Maps, all that is doing is solving a shortest path problem. And this is solving this problem on a dynamically changing network because the congestions on the roads evolve over time. Similarly, if you want to do some computation on your favorite social network, the network keeps changing with time. And what you are asking for essentially is a dynamic algorithm. And this is true in general for any big data applications because the underlying input data is so huge that you cannot just afford to run a static algorithm from scratch after every small change to the input. The second reason is that if you look at communities outside of theoretical computer science, in machine learning or data mining, they do care a lot about some basic computational primitives like least square regressions, community detection over a social network, or clustering and so on. And in most applications where these primitives are useful, the underlying data is evolving dynamically over time. And so it comes as a no surprise that in recent years, even in more applied communities, we are seeing quite a few papers appearing that are essentially dynamic algorithms papers. If you just look at the key theory result, in each of these papers, they are just doing dynamic algorithms. Because all they are doing is showing how to maintain clustering efficiently in a dynamic setting, let's say. The third reason to care about dynamic algorithms is that often fast dynamic algorithms lead to fast static algorithms. So a very basic example here is Dijkstra's algorithm, which uses priority queues as a data structure. And if you just think about it for a bit, priority queues is nothing but a dynamic data structure. So you need a fast dynamic data structure to run Dijkstra's algorithm efficiently. And indeed, one of the very first famous papers in dynamic algorithms was by Slater and Tarjan in the early 80s. It's called a data structure for dynamic trees. And if you just look at the abstract, it just says, using this data structure, new fast algorithms are obtained for the following problems like max flow and other network flow problems. So the very first celebrated result in dynamic algorithms led to fast static algorithms for max flow. Now, fast forward 40 years, just last year we had a breakthrough result, and according to my opinion, this would be rated as among the top 3 algorithmic results in the last 20 years, which obtained an almost linear time algorithm for maximum flow problem. It got huge deal of attention in the theory community, got the best paper award at Fox last year. And if you just look at the abstract again, it just says our algorithm builds the flow using a new dynamic graph data structure. So I assume if you are interested in algorithms, you would care about maximum flow even in the static setting, and if you care about that, you need to know about dynamic graph algorithms. The last reason is you can take any classical optimization problem and ask what is the computational status of this problem in the dynamic setting. And it so happens that despite decades of effort, many of these questions are still unresolved. And you can ask this question for any problem like matching, shortest path, connectivity, min cut, and so on. And as the title of the talk suggests, I will just focus on dynamic matching. So this is the brief motivation for the talk. Now, feel free to interrupt and ask me any questions in between. I'll be very happy to take questions. Now let's go to the next part of the talk. I will start with dynamic matching, some preliminaries. So what is the maximum matching problem? It's a textbook problem in graphs. We are given an input graph G, and a matching M is just a subset of edges that do not share any common endpoint. So here on the right hand side, you can think of a bunch of doctors on the left hand side and hospitals on the right hand side. And these edges or links represents whether a given doctor wants to join a hospital or not. Now, this set of red edges would form a matching because no 2 doctors are being assigned to the same hospital. The size of a matching is simply the number of edges in the matching. And in the static setting, our goal is to find a matching with possibly approximately maximum size. And throughout the talk, I will be dealing with a multiplicative notion of approximation. The approximation ratio would always be greater than or equal to 1. So when I say that a matching M is, let's say, 2 approximation, it means that its size is within a factor 2 of the maximum matching size. In the static setting, the maximum matching problem is extremely well studied. So it's just a textbook problem, and if you just open this textbook by Vazirani on an approximation algorithm, it just says the study of maximum matching led to the development of fundamental techniques for the entire field. So it's natural to ask what happens to the computational status of the problem in the dynamic setting, and that's the focus of the talk. So what is the dynamic matching problem? Let me precisely define it. In one line, we just want to maintain an approximately maximum matching when the underlying graph is changing over time. That's the goal. The precise setting is as follows. Take an input graph G with n nodes, and now we have a dynamic algorithm that is supposed to maintain a matching M in some region of the memory, which we will just call the output memory. And this dynamic algorithm is just handling a sequence of updates. And each update inserts or deletes an edge in the graph. After each update, the algorithm spends some time and then goes ahead and maybe inserts or deletes some edges from this set M, ensuring that M always remains a matching and it always remains an approximately maximum matching. That's the goal. So here, we basically simultaneously want to minimize two things. One, we should have good approximation ratio. So the matching we maintain should be close to optimal always, all the time. And we should have small update time. And there is a trade-off between these two quantities. So our goal is to just study this trade-off. And throughout the talk, I would often focus just on amortized update time. It just means update time on average. So when I say that an algorithm has amortized update time log n, it just means the following. If you take any sequence of t consecutive updates, the total time the algorithm spends on those t updates is at most t log n. Okay. So on some of these individual updates, the algorithms might spend a long time, but on average, the time spent per update is log n. Okay. Any question regarding the problem setup?
So, so you're not really talking about the initializing thing, which I suppose because you can just add edges one at a time, right? So that
very good question. So for initializing thing without loss of generality with amortized update time setting, you can just assume you were starting with an empty graph. Because if you start with a non-empty graph, just insert those edges one at a time. Okay. Good. So this is the problem we want to solve. Now, what is the current literature on this topic? It's really huge. So this is, all these papers appeared within the past 10 or 12 years, a huge chunk of papers, and I don't have time, of course, to list through all these results. But why is it that so many papers have appeared on this single question? Because you can study it from various different perspectives. So you can talk about worst case versus amortized update times, restricted form of updates, deterministic versus randomized algorithms, and so on. But to keep things simple and clean, in this talk, I will just focus on the following two parameters, which I think captures the key challenges in this area. I will just focus on fully dynamic updates. So we allow for both insertions and deletions. And we just want to look at the trade-off between update time and approximation ratio in the setting that I described, so as not to overwhelm you with various details. Now, with this vantage point, what is our ultimate goal in this topic? The ultimate goal is to get this, a 1 plus epsilon approximation dynamic matching algorithm that runs in polynomial in log n and 1 over epsilon update time. Now, why do we care about this particular question? First of all, let's look at the polynomial, the update time bit. Note that an update is just an edge insertion or deletion. It's an n-node graph, so you can specify an update using just log n bits. So when we are asking for polylog n update time, we are asking for update time that is polynomial in the input size. And another way to think about it is this. If you have a polylog n update time dynamic algorithm, it implies a near linear time static algorithm. So to solve the static problem, start with an empty graph, insert the edges one at a time. The total time you will take is near linear in the number of edges. So that's why polylog n threshold is important. And why do we care about 1 plus epsilon approximation? It's because there are strong conditional lower bounds which says getting an exact maximum matching in the dynamic setting is not possible. So you cannot hope to get one approximation. Okay. So with this, let me try to chart out what is the current state of the art. So we look at this chart, the x-axis is the approximation ratio. So this is 1, this is 3/2, this is 2. And the y-axis is the update time. And this O tilde 1 just means some polylog n update time. We are happy with this. Then there is this root n and n. Now this red bar here just represents the lower bound. The lower bound actually tells us that you cannot maintain one approximation or exact maximum matching in better than n update time, n being the number of nodes. So this red region is ruled out. What is known? Basically, there are three main sets of results. The first one says that if you care about 1 plus epsilon approximation, we can actually get n update time. The second one says if you want 1.5 approximation, we can get root n update time. And the third set of results says if you care about 2 approximation, then we can achieve this polylog n update time. And in between, there are some very nice trade-offs between these 2 points. So these trade-offs suggest that you can get some approximation ratio in this place and some update time that is somewhere in between polylog and root n. However, what is more important is, if you just look at this plethora of results, there is a method behind this madness. It's not that these are just isolated bits of results. So what can we say in terms of techniques that are used to achieve these results? There are basically 3 sets of techniques. The first one that gives us 1 plus epsilon approximation is achieved by something called periodic rebuilding. This 1.5 approximation in root n update time is achieved by something called EDCS. So this is the most blunt name imaginable for a very exciting concept. But I won't have time to talk about this in the talk. And finally, all these 2 approximations in polylog update times, they just follow from dynamizing a greedy algorithm. So these are the 3 sets of techniques. So what I'm going to do next is just focus on this result and just give you a complete algorithm to get this n update time. It's going to take only 5 minutes or so, just so that we get a feel for how we design dynamic matching algorithms. So what is this periodic rebuilding technique? The actual result is this. Consider a dynamic graph with maximum degree delta. What do I mean by that? Delta is some parameter, fixed parameter, and the dynamic graph always has maximum degree delta as it undergoes edge updates. Just assume it for now. In this setting, it's known how to get 1 plus epsilon approximation in ordered delta update time. This trivially implies this order n update time algorithm because delta can be at most n always. So how does this work? We just need to start with a basic combinatorial fact that in any graph with m edges, the size of maximum matching is at least m over 2 delta. And why is this true? You just run the basic greedy algorithm for getting a matching. Scan through the edges, take as many edges as you can in your matching. What do you get? Each time you are taking an edge into your matching, let's say you are taking this edge UV highlighted in red in your matching, you are ruling out at most 2 times delta minus 1 edges that can no longer be in your matching. And these 2 times delta minus 1 edges are just potential neighbors of U and V. Because once you take this red edge, you cannot take any other edge incident on U or V in your matching. So it's just a basic counting argument. Each time I take one more edge in my bag, I rule out at most 2 times delta minus 1 many edges. So there are m edges overall. So once I finish this process, I should have at least m over 2 delta many edges in my bag. So opt is at least m over 2 delta, and that's all we need. We don't need anything else. So now the algorithm is this. Think of this time axis. So I'm just thinking of this time as a sequence of updates, okay? You just partition this sequence of updates into phases. So each phase is just a consecutive sequence of updates here, okay? So a phase starts at time t0, then at t1 and so on. How are these phases constructed? It works as follows. At the start of a phase, just compute a 1 plus epsilon approximate matching. Let's call it m init in the graph G. How much time will it take? Using a known static algorithm, this can be done in linear time. Throughout the phase would now last for epsilon times the size of this matching many updates. Throughout this phase, what do? You just lazily output whatever matching you have constructed at the start of the phase. So at the start of the phase, you constructed this matching capital M init, right? So throughout this phase, if an edge from M init gets deleted, throw it away, just output the rest of the matching. That's all you were doing throughout the phase. You were just sitting lazily throughout the phase. And at the end of the phase, you will just go back to step 1. Now, what is the update time during a phase? During a phase, you are not doing anything. So your update time during a phase is constant. So your amortized update time is just the time you spent at the start of the phase divided by the length of the phase, the number of updates in the phase. And what is this quantity? The number of updates in the phase is just this, right? Epsilon times capital M init. And we have already argued that this is at least number of edges in the graph divided by delta. So these two things cancel out and you just get order delta. This is your update time. And why is this giving us 1 plus epsilon approximation? The reason is very simple. Since the phase just lasts for epsilon times M init many updates, the value of opt can decrease by only 1 minus epsilon multiplicative factor during the phase. So whatever estimate you had at the beginning of the phase remains valid throughout the phase. And that's it. Any question regarding this?
Can you maybe quickly just repeat the argument? I kind
Approximation guarantee argument or the?
No, actually the algorithms. I think I kind of missed this notion. So you're looking at the span of queries updates.
So
and you're cutting them into some phase of a particular length. I kind of missed how what.
Okay, so I'll just say something like this. Suppose a new phase starts right now with this update. What do? At this point, run a static algorithm, get 1 plus epsilon approximation in order M time. Now, wait lazily for the next epsilon times size of the matching you have constructed many updates. That's your phase. The phase will end after these many updates.
So you don't do any? Is that the point, that you don't do anything?
Yes. Don't do anything.
You just that's what it means. Okay. You don't do anything.
Yeah.
Okay, I see. So that's why it remains constant. Okay, now I understand. But then you argue that actually this is because of you choose the length of this thing so that it still is an approximation.
Yes,
right?
because opt can change only by a multiplicative
So
1 minus epsilon factor. So you don't need to do anything during the phase. And what is your update time? Just the time you spent at the start of the phase, that's the numerator, divided by the number of updates in the phase.
Right.
Okay. Yeah, so this is it. Now, getting back to this picture here, we actually now completely understand how to get 1 plus epsilon approximation in order in update time. What I will do next briefly is just give you a very high level intuition as to how 2 approximation works in polylog and update time, but I will need to be a bit hand wavy here because these things will become technically very complicated if I want to present the full details. So for 2 approximation, the main approach is dynamic greedy. So you take the greedy algorithm and you try to maintain this thing dynamically. So here is how to think about it. Suppose we just want to maintain a maximal matching. So what is a maximal matching? A matching M is maximal if no more edges can be added to it. So for every unmatched edge, at least one of its endpoint is matched. So these 2 red edges, they form a maximal matching. Because if you take any blue edge, you cannot add it to your matching anymore, because for every blue edge, it has one matched endpoint at least. And in other words, a maximal matching is simply the output of this greedy process, that you are scanning through these edges and you are trying to take as many edges as you can inside your matching. It's known that any maximal matching would give you two approximation. This is very simple to prove. I'll just assume it at face value. And suppose we just want to maintain this. What is the naive approach? We are maintaining a maximal matching. Now an update comes. The update just inserts an edge UV in the graph. What do we need to do? We just check if both U and V are currently unmatched. If yes, add it to our matching. That's it. How much time does it take? It just takes constant time to check this. So handling an insertion is constant time. On the other hand, suppose an edge UV now gets deleted. What do we need to do? If this edge UV was not matched initially, we don't need to do anything. Our existing matching will continue to remain maximal. The bad case is when this edge UV was part of our matching, of course then we need to first remove it from the matching. After that, we need to visit its two endpoints, visit all their neighbors and see if we can rematch these two endpoints to any of their potential neighbors. That's all we are doing. Pick any end, go through each of its two endpoints. For each such endpoint X, find if X has any unmatched neighbor Y. If yes, just match X to Y. Add it to your matching. And at the end, you will just recover a new maximal matching. What is the time taken for this step? It's just proportional to the degrees of U and V, because that many neighbors you might need to scan to check whether you can rematch U or V or not. And degrees of U and V can be as large as order n. So overall you get order n update time. Any question regarding this? Okay, so this is the bottom line. We see how to get two approximation in order n update time. Now here is a question. If I ask you, can you get better than order n update time deterministically for a maximal matching? The answer is no one knows. This trivial algorithm that I presented is the best possible currently for any deterministic algorithm. And I would find it superly interesting if somebody can improve this trivial bound deterministically.
Improve the update time.
Yes, the update time. So you maintain a maximal matching always.
And two approximate, okay.
Yes. But
the maximal matching, yes, just for the maximal matching.
Yeah, maintain a maximal matching deterministically better than this. It's open. And what is very surprising is that the state of the art is just one paragraph. However, if we use randomization, we can do significantly better. Or instead of 2 approximation, if we want 2 plus epsilon approximation, then also we can do significantly better. This is what happens. And so we can do better using 2 separate techniques. One is called randomized greedy, the other one is called fractional matching. I will only just briefly outline the first technique. The second would be outside the scope of the talk. So what is randomized greedy? It's just a variant of this greedy algorithm. And I first define randomized greedy in the static setting. So what is going on is, you take a uniformly random permutation of all the edges in the graph, pi. Now, let m pi denote the output of the static greedy maximal matching algorithm when it visits or scans the edges of E according to this random permutation, not in any arbitrary order. Okay. Once you throw in this randomization, it so happens that you can precisely maintain the output of such a matching in polylog and update time. There is a sequence of very elegant papers, and you can teach them in maybe 2-3 lectures in randomized algorithms which achieves this. But I cannot present the full proof because it will be quite technical. But yeah.
Is it the same random permutation for all updates?
Yeah, for all updates. But the updates need to be oblivious to the source of randomness. Okay. So it's a very clean result to remember that, okay, randomized greedy can be maintained. Yeah. So that means 2 approximate dynamic matching can be maintained in polylog update time with high probability. I'll just show you just one intuition as to why this makes sense, not the formal proof. What is the bad case for this vanilla version of dynamic greedy? The bad case was there is a guy V with very high degree omega n, it had a matched edge Vx, and this matched edge is now getting deleted. And we want to find a new neighbor for V, and the only way we can deal with this right now, despite years of effort, is to just visit all of these neighbors, and that takes order n time. That's the bad case. When you are using randomized greedy, okay, this is all that I said in words right now. When you are doing randomized greedy, this bad event that this red edge gets deleted will occur very infrequently, because roughly speaking, V is picking one of its incident edges uniformly at random to match itself to. And if the updates are oblivious to this source of randomness, at least half of the edges incident on V in expectation needs to be deleted before you hit this bad event. So this bad events in expectation occurs after omega n many deletions. When the bad event occurs, you need to spend order n time, but now you can amortize, because you are spending order n time, you are waiting for omega n updates. But this is a very, very high level intuition as to why this works, not the analysis. Okay. Now, the other approach is fractional matching. Due to time constraint, I will skip this part. I will just give one line summary. This approach, you can think of it in two different ways. One as a de-randomization of the randomized greedy approach at the cost of slightly increasing the approximation guarantee from 2 to 2 plus epsilon. That seems to be the cost we pay for de-randomization. One other way of thinking about this approach is that it's dynamic primal dual algorithms. So in the static setting, primal dual method is a very widely used tool to design algorithms. We are dynamizing the primal dual method. That's one line summary. And now I'll just skip this part due to lack of time.
So, is there anything better known for bipartite graphs? Or?
No. Okay, so we are here. We have seen how this first point works. We have sort of some intuition as to how we achieve this. I'm going to skip this middle point. Now, I'm not too familiar with it, but I think in Chinese calendar, every year is called the year of dragon or the year of something else, right? So from that perspective, this particular year in dynamic algorithms could have been called the year of dynamic matching. Because after a decade of sort of stagnation at these 3 points, very, very recently, all within just last 1 year, we have had improvements across all these 3 points. And these improvements are very tantalizing because they are very, very tiny, but all they are showing is what we knew to be the correct bound until now may no longer be the best answer. Okay? And I have just shown you these particular improvements. Now, one other very intriguing thing is all these new results hold only for value version of the problem. What do I mean by that? These 3 purple dots that I am highlighting here, so this purple dot just says we can do slightly better than 2 in polylog time, slightly better than 3/2 in the same root in update time. We can do 1 plus epsilon in slightly better than in update time. All these 3 recent improvements work only if you just care about the size of the matching that you are maintaining. So the algorithm will just output a value. It will not maintain a set of edges as matching. And there is a deep reason why this is the case. It's not some minor technicality. And using current approaches, you cannot get rid of this assumption. So what I'm going to do now for the next, let's say 15 minutes, is just focus on this bullet point and just try to highlight the main ideas as to how we achieve this. So this result is based on this paper that I had with my student Peter Kish, Thachapal Saranurak from University of Michigan, and David Weiss, who is currently in Google. And this was the main result. So until now, it was known how to get two approximation dynamic matching in polylog n update time. We showed you can do slightly better. 1.99 approximation in polylog n update time, and the main message was that you can do better than greedy in the dynamic setting. That greedy, if you care about polylog n update time algorithm, greedy is not the end of the road. That's the conceptual message. There was an independent and concurrent work by Behnezad. Both these two results work for the value version of the problem only, and both these two papers got the best paper award at SODA 2023. So let me now just give a brief overview of the techniques, and I'm going to assume all kinds of simplifications. I'm going to assume bipartite graph, oblivious adversary, amortized update time, just slightly better than 2 approximation ratio, just to highlight the key idea. So what is the main technical challenge in getting better than 2 approximation in polylog update time? In this particular topic, it's known as the vertex update barrier. And the vertex update barrier is as follows. We know how to get 2 approximation in polylog time already. What is the most natural approach for getting slightly better than 2 approximation? The most natural approach is this. I will first maintain a maximal matching, which I already know how to maintain. Then I will try to augment this maximal matching by maintaining another matching, and by using just length 3 augmenting paths if needed. And at a very high level then, the approach is maintain this maximal matching M1 using previous work in polylog update time already. Then look at this graph between matched nodes in M1 and unmatched nodes in M1. Try to find another matching in this graph G prime. So G prime is basically the edges crossing between matched and free nodes in M1. Try to maintain a matching M prime in G prime that is large enough, and then augment M1 along with M prime to get slightly better than 2 approximation. Now the question is, why can't we maintain such a matching M prime and in G prime? The one line answer is, look at how this graph G prime is evolving. If there is an edge update in M1 in this red matching, there will be a vertex update in G prime. Because if this node, if you say delete this matched edge, this node is now becoming free and it will lose out on lots of existing edges in G prime. And so far, we never knew how to maintain a large matching under vertex updates, because vertex updates are way more challenging than edge updates, because with one vertex update you can potentially insert n edges into your graph. And now you can spend countless hours, as I had also, thinking about how to break this vertex update barrier, maybe massaging this framework a bit and so on, but it just doesn't work. And this is where it stood for several years. The main technical challenge that we overcame was to basically circumvent this vertex update barrier. And if you want to remember just one slide of take-home message as far as the techniques are concerned, it's this. We are using 3 facts. You just need to know 3 facts. One, that there is a very cool sublinear algorithm for matching, which was already available. And I will explain what it means just in a bit. That there is a very nice vertex versification procedure which says we can look at a restricted class of inputs. This was also already available. And the third was that there is a very nice semi-streaming algorithm. It's a different model of computation. You don't need to understand the definition if you haven't encountered this before. But there was a nice semi-streaming algorithm for matching. And if you just stare at these 3 facts together, it sort of becomes apparent what you need to do. You just get our result. And with hindsight, it was relatively very simple. And I remember that basically when we first realized that, okay, this gives us the result, I had 2 competing thoughts in my head. One is captured by this code, that all we need to know is where to find something when we need it. That's a nice conceptual message. And the other was this scene from a recent movie called The Glass Onion. Okay. Now, let's just recap these three facts. A sublinear algorithm. This is again not a technically true statement, but morally this is true. There is a very nice algorithm by Sohail Benezat 2-3 years back, which just says this. We have a graph that resides in output memory. We cannot even read the entire graph. We can access it only by using adjacency matrix queries. Then still we can form a 1 plus epsilon approximate estimate of maximal matching size of that graph in order n polylog n time. And why it is sublinear? Recall that n is the number of nodes, where the number of edges can be as large as n square. So we don't even need to read all the edges to form an estimate of the value of the maximal matching. And this only works for the value version. In the sublinear world, there is no lower bounds which says that you cannot return a matching in sublinear time. The next fact is a vertex falsification procedure, which just says that without loss of generality in the dynamic setting, you can assume that you are dealing with only those kind of dynamic graphs which always have large matchings. By how large? Let's say opt is always n over 1000 at all times. Now, this does not do the job for you yet, right? Because if you are just given the guarantee that opt is always at least n over 1000, you can say that, okay, I will always output n over 1000, but you get 1000 approximation. You need 1 plus epsilon approximation. And the third fact is a semi-streaming algorithm. Again, you can forget about the semi-streaming model. The template algorithm looks like this. Think of B as being some large constant, let's say 10 or 100, and delta as some parameter that is some very small constant, let's say 0.001. The algorithm looks like this. You first compute a maximal matching, M1, highlighted in red. Then, in the next round, you compute a maximal B matching between the matched nodes in M1 and unmatched nodes in M1. So what is happening for this B matching M2? Look at the matched nodes in M1, you give them capacity 1. The unmatched nodes in M1, you give them capacity B. B is some large constant. And when we are saying B matching, it just means a node here can be matched B times, whereas a node here can be matched only once. So in second round, you just compute a maximal B matching. And now you take convex combination of the sizes of these two matchings depending on delta. And this actually would give you better than 2 approximation. This is a very useful fact to know. Now, this result was actually sort of known in the semi-streaming community in a series of previous papers. We refined it, made it, probably improved some of the constants, but the framework was already there. Once you know that this algorithm gives better than 2 approximation, how can you make it dynamic? I will skip the proof, okay? So just take it from me that this gives better than 1.99 approximation. Yeah.
So why is this? So can you give some intuition why this is possible? Because surprising, because M2 is not a matching but just a B matching. So
I can.
Is there still a good?
I very well can. I actually have 5 slides.
Okay.
But let's take this offline because I will like to just finish the talk. And yeah, so these are my slides for the proof. I can go through this offline. Okay. So let's just see what the implications are. If you want to maintain 1.99 approximation in the dynamic setting now, what should we do? Okay, this M1, this red matching, just maintain it using previous work. This is just a maximal matching, polylog update time. The challenge is maintaining the size of M2. We don't even need to maintain M2. We only need the size of M2. That's the key take-home message from this point above. That mu is an estimate that depends only on the sizes of M1 and M2. So how do we maintain the size of M2? Note that if you just want to maintain M2, you will get stuck with the vertex update barrier again, because M2 is being defined on a graph which changes by vertex updates. So how do you bypass this? Now we invoke the sublinear algorithm. So to put everything together, the main challenge is to maintain the size of M2. So again, just think of the time axis as a sequence of updates. We will again work in phases. Now each phase will last only for epsilon n updates, n being the number of nodes. What do we know from the vertex classification procedure? We have the guarantee that opt is always at least n over 1000. So if a phase is epsilon n long, opt changes by at most a multiplicative 1 plus epsilon factor within a phase. So if we have a good estimate of opt in the start of a phase, we can just sit idle throughout the phase. That's all that we will exploit from here. Now, at the start of the phase T0, you just compute the size of M2 using the sublinear algorithm of Sohail-Pei-Darwaz. It takes order n time. And this is where it's key that we can only compute the value, because the sublinear algorithm won't be able to give us the matching M2. It will only give us the size of M2. So we do this in order n time at the start of the phase. Then at the start of the phase, we just apply our formula for mu, take the convex combination of size of M1 and M2, and we know that mu is 1.99 approximation at the start of the phase, and mu remains 1.99 approximation throughout the phase, because during the phase opt hasn't dropped much at all. So if we have a good estimate at the start, we have a good estimate throughout the phase. And now what is the update time? Okay, M1 we are already maintaining. So what else is going on during the phase? At the start of the phase, we are just computing size of M2. It takes n polylog n time. The phase lasts for epsilon n updates. So the amortized update time is polylog. And that's it. Okay, any question regarding the proof sketch? Okay, good. So now to conclude, let me just say that this actually points to some very interesting connections to sublinear algorithms literature. What are these connections? Recall this vertex classification lemma that I just stated, that we can just assume that opt remains at least n over 1000 at all times. Using this, we can now actually rederive this first result by Gupta and Peng, which we went through towards the middle of the talk, that we can get 1 plus or maintain 1 plus epsilon approximation in n update time. How? Again, we run in phases. At the start of a phase, you compute a 1 plus epsilon approximation estimate mu of opt. How much time will it take? Linear in the number of edges. Number of edges is n squared, so you are spending at most n squared time. Now the phase will last for epsilon n many updates. So keep outputting the same estimate for epsilon n updates. You are still good because opt is always at least n over 1000. So in a phase, opt changes by at most 1 plus epsilon n, 1 plus epsilon multiplicative factor. So your approximation guarantee is still good. And repeat. That's it. So just run a static algorithm, output the estimate, stay idle for the next epsilon n updates, repeat. This is the algorithm. This gives 1 plus epsilon approximation. And what is the update time? At the start of the phase, you are spending n squared time. The phase lasts for epsilon n. So the update time is order n. And that's the Gupta-Peng result. Okay? Just a 3-line proof. Now, what we very recently showed was this first line, that compute a 1 plus epsilon approximate mu of opt. Instead of n squared time, we can do it in n to power 1.99 time. This is a very recent result that's currently under submission. And this is just a sublinear algorithm. There is nothing dynamic going on in here. You just want to get a 1 plus epsilon approximate estimate of maximum matching size in better than n square time. This is what we get. And that now immediately implies, if you just follow this framework, what is your amortized update time? At the start of the phase, you are spending n to the power 1.99 time. The phase lasts for epsilon n updates. So your amortized update time is now better than n to the power 0.99. So we, as an immediate corollary, we get better dynamic algorithm. Okay, and this is why all these recent improvements work only for the value version, because they are just using sublinear algorithms as subroutines, and those guys can only deal with value version of the problem. So what are the open questions from here? To conclude, this is the current state of the art. 1 plus epsilon approximation in n update time, 1.5 approximation in root n update time, and 2 approximation in polylog n update time. The very recent work is none of these bounds seem to be the best possible bounds if we stick with the value version of the problem. So two very natural and I also think very hard open questions that I have no clue about are the following. A, can we make these results work for the search version of the problem? Let's say, can we get 1.99 approximation when we are actually maintaining a matching, not just its value? The current approach will not work. We will need completely different ideas. And the second one is, if we just stick with this 1.001 approximation or 1 plus epsilon approximation regime, what is the best bound here? Can we actually even get polylog update time, or can we get a better lower bound? Nobody knows. Okay, and I would say that these two are the major open questions in dynamic matching right now. So this concludes my talk. Thank you. I'll be happy to take questions.
Question?
So with weights, it's much harder.
Okay, so there is actually a generic reduction by Arden, Bernstein and others, which shows that if you have, let's say, an F update time algorithm for the unweighted matching problem, you can make it work for dynamic weighted matching, but you get a 1 plus epsilon factor blow up in approximation ratio and a exponential or maybe doubly exponential in 1 over epsilon blow up in the update time. And this reduction works generically only for bipartite graphs. For general graphs, on a case by case basis, it has been observed that this reduction works. But that I think is also another very interesting open question. For general graphs, can somebody give a reduction from dynamic unweighted matching to dynamic weighted matching?
So I have a question. Is there anything known about the worst case update times for these guys?
Oh, okay. So this one we can make it worst case. This one also we can make it worst case, and I am pretty sure that this one would also be worst case.
Mm-hmm.
So getting worst case update time is not the main challenge here, I would say. Because the thing is, most of the time when you are doing something like periodic rebuilding, you can make it worst case with some extra effort.
But what about your recent result? So as I understand, like all this algorithm work a lot, then wait, then work a lot, wait.
Yes.
So are you going to, while you are waiting, you sort of like also work?
Yeah, while you are waiting, just in the background, you just keep working a little bit after every update.
There is no black box kind of thing, right?
There actually is a black box result. So it was basically implicit in, I think, a few previous papers of Danupan and others, and then my student Peter made it explicit in a recent paper in ITCS, I think 2 years back, which just says if you can handle logarithmically many batch updates in amortized update time, good amortized update time, then you can handle everything in worst case polylog update time.
So one of the setting that I've seen this kind of dynamic
dynamic approach like that relates to logic and more.
Mhm.
I mean, is this kind of like work by Thomas Wentig and the idea is in database, then you have your database and then you can
Mhm.
compute some data structure from that, and,
Mhm.
and then you want to maintain the results of queries
Mhm.
when you change the database a bit. So I just think that are the work that's done in your area, are they really just very specific to this kind of matching problems, or is there something there that could like work in more generic like graph problems or?
I would say this, that first of all, in databases, it's not surprising that databases are also changing dynamically, and you can think of databases as some kind of data structures as well, right, where you have some requirements. Whether these techniques will transfer or not, that I will need to see by looking at the specific problem. A limited answer is, in the context of graph algorithms, there are generic techniques that work for multiple different problems in the dynamic world. So just as in the static setting, there are techniques like divide and conquer, greedy, and so on that works. In the dynamic setting, there is dynamic primal dual, expanded decomposition, and there are quite a few others that have been applicable for many different problems. But whether they would be applicable for database problems or not, I cannot say on top of my head.
So if there is no other questions, let's just thank the speaker again.
Thank you.